Hello again, and welcome back again to the Applied Business Statistics course. And in this session, we are going to continue discussing the hypothesis testing topic. We discussed in the last lecture the philosophy behind hypothesis testing, the theory of hypothesis testing, and we have discussed the special case, which is the hypothesis testing around the population mean. In this session, we are going to discuss the hypothesis testing around the population proportion. So this is part three of 4 parts of hypothesis testing topic. We have seen in the last session that we can develop hypothesis tests for the population mean from the sampling distribution of the sample mean. So we are going to use the same idea and the same procedure to develop hypothesis tests for the population proportion from the sample proportion. Now, we have discussed in the first topic the sampling distribution of the population mean and the population proportion. And we know very well what is the sampling distribution of the population proportion. Now, we are going to use this sampling distribution to discuss the hypothesis testing for population proportion using the sample proportion and its sampling distribution. We mentioned in the first topic that if n is very large or relatively large, which means that n times p greater than or equal 5, and n times q greater than or equal 5. Both conditions. Q is 1 minus P. So if both N times P and N times Q are both more than 5, then we can consider N, the sample size, is relatively large. So in this case, the sample proportion, which is P hat, is approximately normally distributed. So we can write down the sampling distribution of P hat, the sample proportion, as Z with mean equals mu of P hat, which is the mean, equals P, and standard error, which is square root of P times Q over N, whereas we mentioned that Q is 1 minus P. So this suggests the Z value as Z equals P hat minus P naught, the null value P naught, over the standard error sigma P hat. This value Z is approximately standard normally distributed, which means it has a standard normal distribution. So that's has standard normal distribution under the null hypothesis H naught P equals P naught. So under the null hypothesis P equals P naught, we expect P to be P naught. Then in this case, this is the expectation. This will be the expected value of P under the null hypothesis. So instead of the expected value, we put P naught, right? Then under the null hypothesis also, the standard error of P hat, which is sigma P hat, will be equals P, the square root of P naught times Q naught over N, and the Q naught is equals 1 minus P naught, and that has that value, the z value, the z value in this case has a standard normal distribution. So we can use the standard normal tables from the statistical tables to obtain the critical values, and we can follow the 6-step procedures of the testing hypothesis problems. We have discussed the procedures for testing hypothesis, and we mentioned that there are 6 steps for conducting hypothesis testing for the mean, and the same procedures can be used to conduct hypothesis tests for the population proportion. Now, to see this, we can solve this example. Example 5, which says in a random sample of 100 units from an assembly line, 15 were defective. Does this constitute sufficient evidence at the 10% significance to conclude that the defective rate among all units exceeds 10%? There is significant evidence to conclude this, that that the defective rate among all units, among the population, exceeds 10%, which we are going to discuss. So we have n equals 100, and we have 15 defectives. So p hat will be 15 over 100. So 50.15, that's the value of p hat. And we have also 10%, which is p naught here, 10% or 0.1 here, which is the p naught. So the first step, the testing hypothesis procedure will be, first step is to write down the null and alternative hypothesis. The alternative hypothesis, which is the one which we are going to prove. The one which we are going to prove is it, or is the defective rate among all units exceed 10%? That means the alternative hypothesis is P is greater than 10%, which is 0.1. 0.1. That's the alternative hypothesis, because we mentioned that the null hypothesis usually use the equal sign. So the null hypothesis is P equals 0.1. So the alternative hypothesis is that P is greater than 0.1. We put the thing which we want to prove in the alternative hypothesis. So we want to have an evidence to reject the null hypothesis in order to prove that the alternative hypothesis is correct. If we reject null hypothesis, then the alternative hypothesis is correct. That's the way to write down the null and alternative hypothesis. Then the next step, if H naught is correct, then n times p will be 10 and n times q are 90. So both have values above 5. One is 10 and the other is 90, so they both are well above 5. So we can consider the sample size is so large, then we can use the normal approximation. So we use the test statistic Z. So we can go through to the third step, which is to decide the significance level. In this example, the significance level, and most examples, the significance level is given. Here, it is 10%. So alpha equals 0.1 or 0.10, 10%. So it is given. So the fourth step is that to decide the to calculate the observed Z actually, and to decide the rejection region, critical values. Before calculating the Z, observed Z, we must compute or find the critical value Z alpha from the Z table or the standard normal table. So the test is right tail test because this sign is greater. So it is right there in big area, large areas. It is in the right hand side. So we can call it right tailed, right tailed. So the Z value from the table using alpha equals 10 will be 1.282. That's from the standard normal the table. The standard normal table, statistical table, we can find this. Notice that we did not divide alpha by 2 because you use here a one-sided test or one tail test Z alpha, not Z half alpha. Only we use Z half alpha in two-sided test or two-tail test. But here it is one-sided test. It is right tail test because the sign is greater than. If it is small, if it is less than, it will be left-tailed and the same value, but will be with minus sign here. And if that value sign is not equal, then we must divide alpha by 2 and obtain Z 5% only, not 10%, which is, and that value will be different from the table. Uh, Calculating this value or obtaining this value, then we must calculate the observed value of the test statistics. And we must reject each node if the observed values of the test is greater than this point, because actually the rejection region or the critical region will be on the right-hand side. So in the big values, large values, we reject the null hypothesis. It's not if the observed Z is greater than 1.282. Now we calculate the observed statistics. So before that, we calculate the standard error, which is the square root of P naught times Q naught over N, which is the square root of 0.1 times 0.9 over 10, which comes to 0.03. That's the standard error. Then we calculate observed Z by P hat minus P naught over sigma P hat, standard error, which is 0.15 minus 0.1 over 0.03, which is 1.667. So this value is greater than the critical value, which was 1.282. So that's the alpha. So we can now, because since it falls in the rejection region, this value falls in the rejection region because it is greater than this value. So we must reject each node at alpha equals 10% significance level. So there is sufficient evidence to conclude that the defective rate is well above 10%. We have found sufficient evidence to reject the null hypothesis so to conclude that the defective rate is above 10%. Now, example 6. The example says a company selling electronic article surveillance device claims that the proportion of all consumers who would never shop in a store again if the store subjected them to a false alarm is 12%. Notice that it doesn't mention greater than or equal, so, or less than. A store considering installing such a device has interviewed a random sample of 100 consumers, the sample size 100, and found that 17 of them would, would not return if they were subjected to a false alarm. Does this sample support the company's claim? What is the company's claim here? That the consumer, all consumers who would never shop in a store if the store subjected them to a false alarm is a 12%. So the problem is, or the claim is that P equals 12% or P doesn't equal 12% with use alpha significance level equals 5% or 0.05. So P hat is 17. You have 17 units over 10, the sample size, 17 over 10, which 100, sorry, 100, that's the sample size. So the p hat, the sample proportion, is 17% or 0.07. That's the row hat, the sample proportion. Then we can follow the 6 steps procedure. The first step was to set up the null and alternative hypothesis. As we mentioned in this example, that the company wanted to test whether P, the population proportion, is 12% or not 12%. Is it equal to 12% or doesn't equal to 12%? That's what the company want to know. Does the population proportion or consumer who would never shop again in this store is it 12% or not 12%? So the null hypothesis in this case is P equals 12% or 0.12, and that the alternative is that P does not equal 12%, 0.12. That's easy. So this is the first step. Then the second step will decide what the sampling distribution is. So we want to know if whether the sample is large or not large. To know that, we must calculate n times p and n times q. And here we find if each note is correct, n times p equals 12 and n times q equals 88. Then we have both of them are equal to, or greater than, sorry, greater than 5. So we can consider the sample size is so large. Then the test statistic which can be used is Z, the standard normal distribution. So, and the third step is to decide upon the significance level, which is given as usually in most examples and most exercises. It is given, and here it is given as alpha equals 5%. The fourth step is to decide about the sampling distribution and the critical values and the critical region. So this test is a two-tailed test, and the critical value to obtain the critical value, we must divide alpha over 2. We have alpha here 5%, we must divide it over 2 and compute or find from the table z half alpha and find it. We can find it from the table like we have found it in other examples before. It was plus or minus 1.96. So that's the value of Z half alpha actually. So that means we can reject H naught if the observed Z is less than minus 1.96 or if it is greater than 1.96. So the fifth step is to calculate the observed statistical test, the observed value of the statistic. And we must start by calculating the standard error, which is for p hat, which is in this case sigma p hat equals square root of p naught times q naught over n. Then it will be equal the square root of 0.12 times 0.88 over 100, which equals to 0.032. That's the standard error. For using this standard error, we can calculate the observed value of Z, which is p hat minus p naught over that standard error which we obtained before, which equals 0.17 minus 0.112 over the standard error, which is 0.032, and the result is that the observed Z equals 1.563. 1.563, and this value which we need to compare it with 1.69. That's in the last step, and this means that this value is less than 1.96, and of course is greater than minus 1.96, which means that so we cannot reject the null hypothesis at 5% significance level. So we can conclude that there is sufficient evidence to there is insufficient evidence, there is not sufficient evidence, there is no sufficient evidence, or there is insufficient evidence to conclude that the proportion of a consumer discouraged by a false alarm is different from 12%. We do not have enough evidence to reject the null hypothesis actually. Now we will talk about the concept of the p-value for statistics, for this statistic and other statistics. There is something in statistics called the p-value, which we want to explain by example. This is useful in all statistical hypothesis testing problems, not only the case of population proportion. It can be used for population mean and other statistics or other tests. All tests, we can use the concept of p-values in all hypothesis testing, which is important. We can understand this concept of the p-value using the following example. Example 7. For the past few years, the example says, for the past few years, the number of customers of a drive-in takeaway restaurant has averaged 20 per hour. Customers of a drive-in takeaway restaurant has averaged 20 per hour with a standard deviation of 3 per hour. So that's mu average for the whole population. Average mu is 20 and the standard deviation sigma is 3. This year, another takeaway restaurant 1 kilometer away opened a drive-in window. The manager of the first shop believes that this will result in a decrease in the number of customers. So the belief is that the average will be less than 20. To test this belief, of course, a random sample of 15 hours showed that the mean number of consumers per hour was 18.6. That's the sample mean. Can we conclude at the 5% level of significance that the manager's belief is correct? The manager belief, what was it? As we mentioned, that this new shop will result in a decrease. So the average will be less than 20. It was 20, and the manager believes that it will be less than 20. So mu will be less than 20. So we have, from historical values, we have mu equals 20 and sigma equals 3. So, and n equals 15. So x bar equals 18.6. And we have 5% significance level. So we follow the as usual, we follow the six-step process. So the first step was to set up the null and alternative hypothesis. So the question suggests that mu equals, it's not, the null hypothesis is mu equals, of course, it is equal mu naught, H naught is mu equals 20, and as the question says, mu, the alternative is mu is less than 20. So that's the thing which we want to test, whether the decrease in that number will happen. So that means mu will be less than 20. So the alternative hypothesis is mu is less than 20. And as usual, the null hypothesis is mu equals 20. The third step is to determine the test statistic and its sampling distribution. And we know that's testing hypothesis around the mean, not the proportion, this one. So, since sigma is known, the test statistic is Z, not T actually. So the third step is to specify the significance level, which is given in this example as alpha equals 5. The fourth step to define the decision rule. So we have this as a left tail test. So because the sign of the alternative hypothesis is less than, which means we look at the smaller values of the test statistic. So it is left tail test. So the entire rejection region is located under the left tail of the sampling distribution. So the critical value from the standard normal table will be obtained using Z alpha, not half alpha, because it is one-sided test. So Z alpha, and it will be with minus sign, and we obtain Z of 5%, which is equals minus 1.645. Minus because it is left tail test. So that means we reject H naught, the null hypothesis, if the value of the test statistic from the sample is smaller than this value. If it is smaller, we reject the null hypothesis. So the fifth step is to take a sample and calculate the value of the test statistic. And we have, as we know, the standard error of x bar is sigma over square root of n. Sigma equals 5 and n equals 15. Then it is 3 over sigma equals 3 and n equals 15. So It is 3 over square root of 15, which equals 0.775. Then we can calculate z as x bar minus mu naught over the standard error of x bar sigma x bar, which is equals 18.7 minus 20 over 0.775, the standard error, which equals minus 1.677. So the sixth step, the final step, will make a statistical decision. And in this case, as we see, that this value is less than this value. It is not much less. It is not much less, but still, this value is less than this value. It is little less than this value. So the conclusion here is to reject the null hypothesis. Although the two values are so close, but it is still less than that. So for this example, actually, what if we change the significance level? It was not actually 5%. If we move a bit this value, if we have another significance level, then we will not be able to reject the null hypothesis. That's fixed actually, but this can be changed if we change the significance level. Then in other cases, this result might produce non-rejection. In this example, by the 5% level, we reject the null hypothesis, but with different significance level, we might be not able to reject. If we take, for example, 10% significance level, then we will not be able to change the to reject the null hypothesis. If we change the significance level from 5% to 10%. So that's the value here. If we change to 10%, and this value will give us here maybe at 10%, sometime either here or here, and that's in between. So if we have 10%, we'll get this value. For 5%, we'll get this value. And this is the critical value. So in some cases, on some significance levels, we reject the null hypothesis. And in other significance levels, we can not reject or accept the null hypothesis. So what will be the correct decision in this case? For this, we may say that if we can calculate this region actually, here from this part 1.64, which is the observed Z, to this area up to the end, if we can calculate the area here under the curve from this to the left, so it will be more than 5%, but less than 10%. It will be more than 5%, but less than 10%. And then in that case, we can say that we can reject the null hypothesis at this value. It could be 7% or 8% or 3%, whatever. So this value is important. We can reject the null hypothesis with the probability equal to this value if we can calculate it actually. Not 5%, not also nor 10%. But we can calculate this exactly. So we can calculate the exact probability, not 5% nor 10%. We can calculate that value of probability, and we can say that we reject the null hypothesis using with false decision error or probability error equals that. And for this value, we calculate it, we call it the p-value. So what's the p-value actually? The p-value is the smallest alpha value, the smallest alpha value, tail area, this area, that would lead to a rejection of the null hypothesis. You know what? That we call the p-value of the hypothesis test, right? This is the tail area corresponding to the observed value of the test statistic from this point to the left. If uh, the observed value on this side, it will be from the observed right. The exact value, which we now calculate it using Excel sheet or using a statistical table or whatever. We can easily now compute this value. So why should we always stick with the statistical tables and find the value from the table exactly as it is? But as long as it is easy now using computers and some statistical programs, statistical programs, or even Microsoft Excel to calculate the exact probability. And we can say sometimes we reject the null hypothesis with p-value equal 0.5 مثلا, or 0.3 or 0.2 or exact value as it is calculated. So we usually reject the null hypothesis if the p-value is small, less than 10% or less than 5% or whatever, less than 1% or any other specified significance level. So if the p-value is less than significance level, then we reject the null hypothesis. If we got p-value 0.6, for example, and we decided that significance level should be 5%, then we cannot reject the null hypothesis in this case. But if we decide the significance level is 5% and the p-value is 0.04, which is 4%, then we reject the null hypothesis, right? Now, what is the p-value for this test? We know that we can calculate, we can reject the null hypothesis for a specific significance level, and we should not be able to reject it for other significance level. But what is the p-value for this? We can calculate it for in this example, not always from the table, but in this example, we can calculate the p-value from the standard normal table. We calculated, we want to write or calculate this area actually. The probability of z less than minus 1.677. Again, we want to calculate the probability is that the probability of z is less than minus 1.677. Again, the probability of z is less than minus 1.677. That is what we call the p-value for this statistic, for this example actually, or this statistical test, right? This area. To calculate this area, because the table gives us this area, so we say that it is half minus this area, z from 0 to 1.677, and that will be 0.0465, which means that the p-value is 0.0465, which is, as we mentioned earlier, it is less than 5%. So we can reject the null hypothesis for if the significance level is 5% in this score. So any significance level higher than this leads to rejection of each node. Right? So this value is small. If the significance level is higher than that, it's okay, we can reject the null hypothesis. If it is two-sided test, or the rejection region is, or the significance level is less than that, we cannot reject. If it is a two-sided test, then we must divide alpha by 2, and then the region will be smaller here. So it will be the region up to the 0.025, not 5%. 0.025, 2.5%, and that will be small. So we cannot reject in this case the null hypothesis. This two-sided test. We cannot reject the null hypothesis using 5% significance level, but we can reject it using 10% significance level. So it is easy in some examples, some cases, using the table, you calculate the p-value. But in other cases, we can calculate it using a statistical program or Microsoft Excel. It is easy. So you do not need to stick with the significance level always. We can, as long as using computers, we can calculate the p-value. So it is better now all the time to calculate the p-value. So the calculation of the p-value depends on whether the statistic is one-tail test or two-tail test. So whether to divide the significance level by 2 or not. If it is two-tailed, then we should divide the alpha by 2. If it is one-tail test, we should not divide it by 2. If the test is one-tail, the p-value is equal to the tail area A corresponding to the observed value of the test statistic. If the two-tailed test, the p-value equals twice the tail area corresponding to the observed value of the test statistic. So in each case, we reject each node if the p-value is smaller than the significance level alpha. Right? Now, another example using Excel sheets now, Microsoft Excel. The example 8. A diet doctor claims that the average Australian is more than 10 kilograms overweight. To test this claim, a random sample of 100 Australians were weighed, and the difference between their actual weight and their ideal weight was calculated. Can we infer at the 5% significance level that the doctor's claim is true? The doctor claim is all Australians are 10 kilograms overweight. So is mu equals 10 or greater than 10? That's the difference between the actual weight and their actual weight and their ideal weight. The difference is 10 or not greater than 10. So the first step in this process or procedure is to decide the null and alternative hypothesis. The null is mu equal 10, and the alternative, as the claims of the doctors, is mu is greater than 10. So it is right tail test. And using Microsoft Excel, we obtain the following results. We obtain these results. The mean is 12.175. Standard deviation is 7. That's all sample statistics here. The sample standard deviation is 7.898. The 10 is the hypothesized mean, and the degrees of freedom of the t-test is 99, and t-statistic is 2.754, and the probability t less than t is 1. Their p-value for one test is 0.004, and t-value for one tail critical, the t-value, is 1.660. The other t-value for two tail, t-value, critical value, p-value is 0.007. The t critical two tail is 1.984. What can we conclude from all these results? That's results of the Microsoft Excel by analyzing the data. By the way, here, usually if we use by ordinary calculator, we can say that whether we use Z value or T value. If the sample size is large, then we use Z. But if you use T, even if the sample size is big, and you use t-test statistic, not Z, the result will be the same. Because we mentioned that the t distribution will be very close to the Z distribution for large N, for large sample size. So if we use Z or T, we get the same result. The same result for N greater than 30. For for large sample sizes greater than 30, T distribution and Z distribution give us the same results. So as long as the Microsoft Excel give us the value of T, not Z, it is okay, no problem. T and Z are exactly the same with very, very small difference. If N is very large, then no problem. So here 100 Australians, N is very large. N is 100, so we can use T distribution. And the T is more accurate than Z. So what we can conclude from this result? X bar is greater than 10, but is larger than, is it large enough to reject H naught? Is X bar large enough to reject H naught? That's what we want to conclude. P-value here is 0.004. So the observed T is 2.76539, which is well above the critical value of T. So we must reject the null hypothesis. So the critical value is 1.660, right? The critical value is 1.660, and the observed t value is 2.754. So we must reject H naught and conclude that at this 5% significance, 5%, because it's very much less than 5% the p-value of significance level, that the average Australian is more than 10 kilograms overweight. So alternatively, we can make use of the p-value for the one-tail statistic. Since alpha or p-value is 0.004, which is very well less than 0.05, so that means we must reject the null hypothesis. The significance level is 0.05, but the p-value is very much less than 0.05. It is 0.004. As long as the p-value is less than the significance level, then we must reject the null hypothesis. That's a rule. We reject the null hypothesis again if the p-value is less than, not need to be very much, if it is little less than the significance level. Again, we reject the null hypothesis if the p-value is less than the significance level. So since both conditions are satisfied, we can reject each node at 5% level, or in this case at even at 1% level actually. Right? Note, on the basis of the Excel t-test output, it's not mu equals mu, we can reject. First, it's not mu equals mu can be rejected. One in favor of we reject the it's not, but we accept the alternative hypothesis. In favor of the alternative hypothesis, mu does not equal mu naught. That is two-sided test. If the absolute value of the observed t is greater than t half alpha, or two-tail p value is less than alpha. The second case, in favor of the alternative hypothesis, if mu less than mu naught, HA mu less than mu naught, if observed t is less than minus t alpha, or observed t less than 0, and one-tail p-value less than alpha. The third case, we reject the null hypothesis in favor of the alternative hypothesis, HA, which is mu is greater than mu naught if observed t is greater than t alpha, or observed t is greater than 0 and one-tail p-value less than alpha. Right? So we look at the p-value. If it is less than alpha or half alpha in two-tail test, so we reject the null hypothesis. Again, we reject the null hypothesis if the p-value is less than alpha, or if it is less than half alpha for two-tailed statistic, or two-tailed for two-tailed hypothesis. They are alternative hypothesis. Right? That's what we need to say about it. Another example, which is the similar, which says, example 9, a market considered profitable by an e-grocery if average order exceed $85. A random sample of orders were taken and the order values recorded. Does the data provide sufficient evidence at 5% level of significance to establish that the market would be profitable? Okay. Here we consider the market profitable by an e-grocer if the average order exceeds 85, and we want to test whether this e-grocer is profitable or not. Profitable if exceeds, if mu is greater than 85. Then the first step is to write down, set up the null and alternative hypothesis. So the null hypothesis is mu equals 85, and the alternative it is here greater. We want to test whether it is greater or not the 85. So the alternative is that mu is greater than 85. The second step, that's the right tail test. So then we do not follow the steps here, but we have the Excel, Microsoft Excel sheet, and we have some results. From these results, we have the mean equals 89.266. Standard deviation, these are sample mean and standard deviation, 17.296. Hypothesis value is 85. Degrees of freedom 48. T statistic is 2.274, and the p-value for one tail equals 0.013, 0.013, which is less than 0.05, less than 5%. The critical t-value for one tail also is 1.663, and the p-value for two tails is 0.026, and the critical t-value is 1.989. 1.989. The t statistic is here. That's the observed t is 2.274, and it is greater than both values. And the p-value, two values here, is the p-value is less than 5%. Here it is one-sided test, though, so we do not divide the alpha by 2. We do not take half alpha. So once we look at the one-sided tail or one-tail test, which is this. So that p-value is much less than the alpha significance level, which is 5%. So we can conclude from this result that we reject the null hypothesis note at 5% level of significance and conclude that the market would be profitable. So we reject the null hypothesis and we conclude that the market would be profitable. That's what I would like to say for this session, and thank you very much, and see you on the next and last session on hypothesis testing. Bye bye.